Hi, this is Professor Dorr. In this video, I'm going to show you how to enter a schematic and design a PC board using the public domain program KiCad. KiCad can be downloaded from the website, from KiCad's website. It's a public domain program, so it costs you nothing, and it's been getting increasingly popular in the last few years. I've used it for quite a few projects now, and I'm very happy with it. Now in this video, I'm not going to do a deep dive into all of KiCad's features. Instead, I'm going to show you how to use it just enough so that you can do a small and simple project. And I've picked a project that will be somewhat similar to the mini projects that you're going to do in my senior design class. In other words, I've picked components that you'll typically use, and I've picked things like wire pads and components that have multiple units in the same package. So hopefully this lecture or this video will give you what you need to get through your mini project. And as you head toward your senior design project, you'll probably have to learn a little bit more. But hopefully this will give you a good start. Let's take a look at the project that we're actually going to do. And since we'll be looking at it for a while, let's take a look at it and see what it does. You can see a couple of things here. First of all, you can see a pretty ratty schematic that Professor Dorr drew. It has lots of good eraser marks on it, like most Professor Dorr's schematics do. But let's start off over here. It looks like I want to use a battery, and it's going to be a 9-volt battery, and that's where we're going to get power. So on my schematic, you can see I'm showing that I'm going to have a connection for a battery here, and then I'm going to have a connection to ground here. And on our printed circuit board, we're going to put what's called a wire pad here and a wire pad here, and we'll maybe even mark them battery and ground on the printed circuit board so we can see what goes there. And those will have red and black wires that will probably attach to them, and then they'll go over to our 9-volt battery. Now here you can see a little jumper. I drew it as a jumper, and the idea here is that this jumper is actually going to be 2 little pins that stick up on the PC board. And if you want to make this connection, you put the little cover over the pins or the little shorting clip, and it will make this connection. When you don't want power to be applied to the circuit, you just remove this connection and then throw the circuit in your backpack, and it won't wear the battery down when you're not using it. So we're going to actually put these little pins on the schematic, and we're going to make sure we use the right kind of pins on the PC board, and we get them the right distance so that little shorting plug will fit just perfectly. Now here you can see that I've labeled this, we're going to call it a net or a connection between things, and I have a little arrow that says 9 volts. And you've seen this in schematics before. What I'm doing is saying, I don't want to draw a wire that goes to everything that I want connected to 9 volts. Or in other words, I don't want to draw a wire over to here, and I don't want to draw a wire over here, because that's going to kind of complicate my schematic. So I just put a little arrow and say 9 volts. And then here I say, connect this to 9 volts. And I say, connect this to 9 volts. Same thing with ground, but with ground I use a symbol. So here I have the little ground symbol, and what that means is that this ground is connected to this ground, is connected to this ground, is connected to this ground. What's that do for my schematic? It allows me to just show the stuff that's really important and not have all these extraneous lines. Now let's look at the integrated circuit that I used in this design. I used an LM339 comparator. These parts are pretty common for mini projects. They're pretty common for senior design projects. They're just darned useful little things. And what this part does is it compares the analog voltage at the plus terminal and the minus terminal. And if the voltage at the plus terminal is higher than the minus terminal, the output is a logic high. And if the plus terminal is at a lower voltage than the minus terminal, then we get a logic low. And the reason that I used this part is because these 4 units are all housed in one IC package. We call it a multi-unit part. So when we do our schematic, we're going to have to assign which pins go to this one, which pins go to that one, which pins go to this one, etc. And we're going to have to deal with that on our PC board too. It's called a multi-unit part. And you'll see the same sort of thing with op amps or AND gates or OR gates or NAND and NOR because they're more common. And I wanted to give you an example of actually doing this. While we're at it, let me give you a little bit of insight about the LM339 comparator, because I see students make mistakes with these frequently. We said that when the positive terminal has a higher voltage than the negative terminal, we get a logic 1 output or a high. And if the negative terminal is above the positive terminal, we get a logic low. Now, this part is called an open collector part. And that's really important because if we look at this output right here, we take a look inside the IC, we're going to see an NPN transistor. And the emitter of that transistor is connected to ground, and the base goes back into the IC, but the collector is what is connected to the output. And this part will either saturate that output transistor or it will cut it off. So if the transistor is saturated, of course, it can eat quite a bit of current going down toward ground and with a low output voltage. So we say it can sink current. But if I now turn this transistor off, then I can't supply current because that NPN transistor won't supply current. So the take-home message is that your LM339 can sink current, but it can't source it. So did I connect my LEDs the right way? Well, I've got 9 volts here, and I've got a little current limiting resistor. And if this transistor saturates, then I'm going to get current down through here, and my LED will turn on. If this transistor is turned off, then I will get no current here because I'm going to be looking into a collector of a transistor that's turned off, and the LED will be off. So it looks like I've connected this correctly. Now, what I want this circuit to do is I want it to tell me how much input voltage I have at the wiper of this pot. So you can see that what I've done is I've drawn a 10K potentiometer. It's a terrible drawing of a 10K potentiometer, but hey, that's where ideas get started. And so here's my wiper, and as I move that wiper, the voltage at this wiper is going to go up or down depending how I adjust it. And you can see I've connected it to all the negative terminals. There's actually a wire here. You just can't see it because apparently I erased it and then forgot to put it back in, but you can see kind of where it was. And so it goes to the negative terminal. Looks like I made a mistake here, but it's supposed to go to the negative terminal. We'll have to fix that later, of all these parts. And then here I have a little voltage divider. And my voltage divider is 1K, 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 and then 5K. So if you do the math, if you look at the voltage at this point, you'll get 1 volt, 2 volts, 3 volts, 4 volts going up this voltage divider. And here I drew my resistor as 5K, but I know that resistors don't come in 5K size. So I just kind of noted that it's going to be 4.7K plus 300, because those are two sizes that I can just find in a drawer. So there'll actually be two resistors here. So the basic idea again is when this wiper is above 1 volt, this light will go on. When it's above 2 volts, both of these lights will be on. When it's above 3, all three of them here will be on. When it's above 4 volts, all 4 lights will be on. But remember, to turn the light on, the logic has to be low here. And that's why I'm feeding my input, at least for the ones that I drew correctly, into the negative terminal. If that makes you uncomfortable, stop the video, especially if you're going to use an LM339 or a 393, which is just two of them in one package, in your design. Make sure you're comfortable with that logic, because I see a lot of mistakes with that. Now let's look at our resistor here. So I did just a few little calculations here, and I said LED is going to be about 2.5 volts, and I'd like about 20 milliamps through it. How do I know that? Just experience, kind of experience you're going to pick up when you get into industry. So I say, what resistor do I use? And I say 9 minus 2.5, that's the voltage across the resistor, divided by the 20 milliamps that I want going through that LED. So of course it's also going to go through the resistor, 325 ohms. Standard size is 330 ohms. How do I know that? I just know that because I've done this for a long time, and you will too. But 330 is a standard 5% resistor size. So I know I need a 325 ohm, 330, what's a few ohms between friends, right here. But I better make sure I understand how big of a resistor I need, or in other words, what its power dissipation is going to be. So I say I squared R is going to be my 20 milliamps times 325 ohms. It's going to be 0.13 watts. I know that the through-hole resistors in our drawers in the lab are 1/4 watt resistors. So I'm going to stress them a little bit. Don't do this in your senior design. In your senior design, if you're going to dissipate 130 milliwatts, use something that's about twice the rating, so maybe a 1/2 watt resistor. But we'll have a teachable moment when these get a little warm if we actually build this in the lab. But the important thing is I'm dealing with this now because when I lay out the board, I need to know how big that resistor is going to be. So it's important to get that nailed down here. So what do I have? I have a pretty ugly schematic, but it really gets the point across. It kind of shows me that I'm going to have my jumper here, and then I'm going to have 9 volts. It's going to go to a few places. I'm going to have an LM339, a few diodes. I'm going to need a few wire pads here. I'm going to use a potentiometer, and easy to draw a potentiometer, but I got to figure out exactly which one I need because I'm going to need to lay down the right footprint on my board. So our next step from here is we're going to actually draw this schematic in KiCad. Okay, so now hopefully you have downloaded KiCad. The version that I'm using is, you can see it up here, 5.1.6-1. And yours might be slightly newer, but they all work the same. Sometimes there are small differences in the libraries, and you may run into that, but they're pretty easy to work out. So what we see here is, here's the basic screen, and we've got our schematic tool, and we've got our PC tool, and then we've got some other tools that we'll get to later. But this is kind of the highest screen. So what we're going to do is we're going to open a project. And a project in KiCad has your schematic, it has your PC board, but it also has all the footprints of all the components that you're going to use for the PC board, and that is all encompassed in the project. So what we'll do is say File, New Project, and we are now going to have to find where we want to put that. So we select our directory, and I give it a name, and I tell it to save. So now we're still at the high-level screen for KiCad, but it knows that we are doing a project. So the first thing we're going to do is we're going to make our schematic. So I'm going to click on the schematic tool here, and it's giving me a blank schematic. And you can see I have lots of cool stuff here. I have a grid that I can use if I want. You can kind of see the little grid dots there. We can work in inches or millimeters if we want. And then here are our tools. Here's where we'll place a part, or we'll draw a wire, or we'll draw a connection or something like that. But before we get started, I want to make sure that my project fits on an 8.5 by 11 sheet of paper. So what I'm going to do is I'm going to go up to the page settings, and I'm going to go here, and I'm going to say size A, 8.5 by 11. That's me. So I'm going to set that, and I can put all kinds of cool stuff here. Let's do the issue date, and it gives me the option of today's date. Let's do that. Let's call this revision A, and we'll say this is going to be KiCad tutorial. Dorr. And so now I'll say OK. And you can see that it put my information down here. And if I want to zoom in, I just roll my mouse a little bit, and you can see it here. Here's my title, shows my size, shows the date, shows the version of KiCad I'm using. And I'm going to roll my mouse out. And while we're rolling the mouse, let's look at one cool thing about KiCad is in order to move around in KiCad, you can use the sliders here if you want. And I did that for a long time because I'm an old person and I didn't know any better. But in reality, what you can do is just put your cursor somewhere, roll with your mouse, and it will expand around the cursor. So let's say I really want to look over here somewhere. What I'm going to do is I'm going to zoom out. I'm going to put my cursor here, and now I'm here. So I can do it just with the mouse wheel, and that is really convenient. Before I start drawing parts, there's one more thing I want to do, which is I want to set up my grid. And what the schematic editor will do is it will only draw on the grid points. So we need to be careful about how we set them, because if we have the grid set to one spacing, and then we change the grid over here and we try to draw a wire in, it's really frustrating because it won't let you actually connect to things. So what I do is I set up my grid right up front. So I'm going to right click my mouse. It's going to give me a grid option, and you can see I'm in inches here. You can use millimeters if you want, just be consistent. And I'll say grid, and let's set the grid to 25 mils. That's 25 thousandths of an inch. That that's fine enough that we can work with that. You can see if I really zoom in, see how I can actually see my grid? You can actually see it there. So our strategy for the schematic, I mean, where do we start? And the way I like to draw a schematic is I just like to throw all the parts down because I want to see kind of how big the parts are going to be and how well I need to space them out. And I can visualize all the lines between the parts once I have the parts down. So what I'm going to do is kind of just try to throw the parts down first. And then we'll move the parts where we want them, and then we'll connect them up. So to put down a part, let's get it a little bigger. I'm going to go over to my right menu, and this is my place symbol tool. So I'm going to say place a symbol, and it's kind of saying where do you want to place it, and I'll just click over here, and I get my options. Look at all these cool things I can place. Now, for some reason, KiCad classifies resistors as a device. If you want, you can do a search, but I just know where they are, so I'm going to go right to it. Look at all this cool stuff. So I'm going to go to Device, and then I'm going to go down, and I'm looking for resistors. Q's, R. So here I've got just a simple resistor. There are other kinds of resistors. For example, here's a resistor network. Look, it lets me preview it. I don't want that. Here's a different resistor network. Here's a trimmer resistor. All kinds of cool stuff. But we're just going to use a basic resistor. So they just call it R. And it shows me a picture of it. And I say, I like that. So I'll say OK. And now I can put my resistor in here. Now, if we go back to our little hand-drawn schematic, we know that we have 1, 2, 3, 4, 5, 6 resistors in our little voltage divider. So let's just kind of throw them in here. We knew they were kind of about here on the page. There's 1. And now I'll say, give me another component. So I'll just click with my left button, and it's going to give me my recently used, and that's what I want. So I'll put that there. Not too worried about where they go for right now. Let's go back so that we get out of our placement tool, and we're going to put the other ones down just by copying. So what I'm going to do is I'm going to just go over to this resistor, and I'm going to say C on the keyboard, and look, I get another one. And how many did I want? 1, 2, 3, 4, 5, 6. So 1, 2, let's copy this one. 3, 4, copy with a C. 5, copy again. 6. So I just kind of threw them down. If we go back to our picture, we just put 2 down here because they're in series, because it's 4.7K plus 300. Got one here, 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 here. And we know we need some resistors over here too. So let's put those in. So we'll go back into KiCad, and I'm going to say I need more resistors, and I don't really feel like going to the Place Components tool. So I'll just hover over this and say C. And look, my resistor is there, but I want it to go the other way. So in other words, I want it to be horizontal, so I'm going to hit the R key, R. rotate. So let's say it goes somewhere over here. Now let's copy this one. There's our next LED. There's our next LED. There's our next LED. As I was putting these resistors in, I was thinking LEDs because I was thinking the resistors go right next to the LEDs. So that was why I said that here's this LED, this LED. But what we're doing is putting down resistors. But now let's put down the LEDs. So we'll go back to KiCad. And remember, we're in the schematic part of the program now. We're not in the main part. For example, see if I want, I can look at the overall project. Let's go back into the schematic. So let's put in the LEDs. So I'm going to go to the component sort or the symbol placing tool, pick that tool, and you can see recently used was the resistor. And we knew that I knew that the resistor lived in the devices library down here, but let's pretend like we don't know that for the LED. So we'll just go up here and say LED and look at that. So if we want, we can kind of look around here. Here's an LED with an anode, blue, green. It's a specialized part. Here's a different symbol for an LED. But the basic one here is going to work for us. And so what we'll do is we'll say, okay, so now this thing is all ready to pop an LED down. So we'll put one here. And now I'm going to go back to the selector tool and just say copy. Give me another one. Give me another LED. And give me another LED. And those are our 4 LEDs. Now I just want to reiterate here that we're drawing a schematic. And all I care about right now is that I get my symbols in place. Or in other words, I just want to make sure this looks like a schematic. Because once we get the schematic done, then we're going to associate all these components with what we call footprints, which are the things that go on the PC board. But for right now, we're just trying to make our schematic. Now let's put in the comparators. And let's do a quick look at our schematic, and we can see that the 4 comparators are here. And we see that I kind of showed that 9 volts is going to go into the power pin of this one, and we're going to have ground down here. And even though it shows like it goes into this particular comparator in the package, it really goes into the whole package and powers all the units, just as this ground is the same for all the units. So what you notice here is the way I show them, I have the minus at the top and the plus on the bottom. And we're going to see that we're going to have to do something special to do that. So let's lay these comparators into our schematic. So we go back into our schematic program, and I'm going to pick my place symbol tool. And let's use the filter again, even though it shows up here in recently used because I just checked it. Let's start from scratch. I'm going to say LM339. And here we go. So quad differential comparator. And this shows the packages, but we're not going to worry about that now. We just want a schematic symbol. So let's expand it because we know there are 4 of them in that case. And I see Unit A, Unit B, Unit C, Unit D, and Unit E. That's 5 things. Turns out A, B, C, and D are going to be the different units. And Unit E is what's going to allow us to do the power and ground pins. So let's start off with Unit A. And you can see that for Unit A, here we can move this over a little bit, maybe not. What did I do? Okay, for Unit A, Pin 5 is the plus, pin 4 is the minus, pin 2 is the output. Let's go to unit B. Now pin 7 is the plus, so it's a different unit. Unit C, pin 11 is the plus. Let's take a look at unit E. Unit E just shows power and ground, and we'll put that in last. So let's put in unit A. And so I'll say I like that. And it's going to be somewhere around here. Let's go to unit B. So you notice I just clicked here because I still have my symbol placing tool. So I just click and I'll say, give me unit B. And we'll put unit B over here. Obviously these guys are too close together, so I'm glad I didn't waste any time wiring them up. And now let's put in unit C. And we'll just kind of put that in there. And then unit D. Put it down here. I'm actually going to put this a little bit further down for now. You'll see why in a second. But what you can see is that I have the 4 devices of the LM339, and you can see all their pinouts are different, of course, because they're different comparators. But now I'm going to put in the power pins. What I'd like to do is do it like I have my schematic here, where I have this one up on the top of the top one and this one on the bottom of the bottom one. Of course, in the old days when we drew schematics by hand, this is how we did it. And I'm sure there's a way to do that in KiCad. And when any of you figure that out, make sure you come and tell me, because I'll appreciate it. But I don't know how to do it, so I'm going to do what I do know how to do. And I'm going to go back to my selector tool, and I'm going to put my power and ground pins just on this device here. So in order to do that, here, let's bring them up first. We'll actually go back to the component selector, and let's get unit E, and let's put it on there. And what we really want to do is kind of lay it on just about like this. But things are a little too busy, so I'll put it here for now. And I'm going to just move these parts down. So I'll go to my selecting tool, and I'll just say M on the keyboard, M, and then click to make it stop, M. Good. Now I can put this on top of this LM339. Let's zoom in a bit. I'll do that with my mouse wheel. And you know what I'll do just to center it up is I'll put my cursor here. I'll zoom out, I'll zoom in, and now this is right in the center. So let's now move our E symbol, which is our power symbol. And to do that, I'll type M, and I'll move it down here. And I'm not really connecting anything, I'm just moving the symbol. So let's put it somewhere like that. Yeah, it looks like I was a little bit too low. Let's go up a little bit. All right, that looks a little better. Looks like a mess to me though. So what we're going to do is we're going to kind of clean things up. Let's look at the properties of this E symbol, which are the power and ground. I really don't need the reference designator because I kind of know where it goes, and I don't really need to be told it's an LM339. So here's what we're going to do. I'm going to right click here, and I'm going to go to properties and say edit properties. So here is the symbol that I just selected. So reference designator, show, nah, I don't want to see that. Value, I don't want to see that either. So now we'll say OK. And now you can see that I removed those properties for this E component. Here, I'll show you. Let's move it. I clicked too close to two things, so it's asking me which one I want to move. So let's see, I'll actually just go down here, tell it I want that one. And you can see now, this doesn't show the LM339 or reference designator anymore. I'm kind of liking the V plus and V minus. So I'm going to leave those for now. So I'm going to go M, bring them back, kind of put them in here. That's not too bad. And let's clean this symbol up just a little more. What I'm going to do is just move this out of the way. So I'm going to go M, and it caught the LM339. And this is the reference designator, which of course this schematic doesn't know about reference designators yet. So it's still just a question mark. Let's do another, let's leave that V plus and V minus there for right now. Now, let's take another look at our LM339s here. They have the plus on the top and the minus on the bottom. Let's go to our schematic, and I have the minus on the top and the plus on the bottom. So let's fix that. So what I'm going to do, I'm going to click on the component, and you can see that I've clicked on it because it's telling me right here which one I'm looking at. Like for example, if I went to the resistor, now it's telling me I'm on the resistor, but I'm on the LM339. So what I want to do is I want to go right click, orientation, and I'm going to mirror this around the horizontal axis. Lots of words. I really like the picture. So here we go. Look at that. Now the minus is on top. Let's do that with the others. Now, am I going to slide this down? I could if I wanted, but I'd rather just zoom out and then zoom in around these ones, just because it's faster, but you don't have to do that. Right click. Let's see, orientation, mirror around the horizontal. Let's do this one, orientation, mirror around the horizontal. Can't see this one, so I'm just going to zoom out, and then I'm going to zoom in, and it's right in the center now. Orientation, mirror around the horizontal. Okay, so now I've got my LM339 looking pretty good. The next component I want to throw down is the potentiometer, this component right here. So what we do is we get our symbol placer, and I click anywhere in the schematic, and what I want is a pot. So let's do it this way. So here is a potentiometer, and I don't like that potentiometer, so I'm going to look a little bit more. Okay, so I'll say pot. And I'm going to look through the choices I have. And if I just click over here, I can look and see what I'm going to get. So here's a potentiometer. That's not bad. It's got a wiper here, and it's got that European resistor symbol. It doesn't have the little squiggly lines that we're used to, which really isn't bad because we kind of use those European symbols up here anyway. But let's keep looking. Dual potentiometer, that's kind of cool, but that's not us. Small, nah. Trim, nah, I don't like that. I want the wiper with the arrow. Okay, no arrow there. Look at that, RPOT US. I'm kind of liking this one. I could have used the other ones also, but I kind of like this one, so let's use it. So we say okay, and we know that it goes somewhere here in our schematic. Next, I want to place the connectors. We can see that we're going to have a connector out here, which is where we're going to connect our battery, and then we're going to have a ground connector. Of course, when we look at the PC board here, this is going to be like a wire pad, and we're going to probably solder a red wire onto it, and here we're going to put a black wire. And then I'm going to need a connector here, And this one will look a little bit different because I kind of want it to look like this. So let's put those into the schematic. So we want to place a symbol, and I'll just click over here somewhere. And I'm looking for connectors, and I don't really need anything real specific. If I go over here, I'm going to get different manufacturers' connectors, which is really cool because some of those connector symbols can get pretty complex, and they're already here in KiCad. I just want generic connectors. So let's take a look. Here I have a connector just one by one. That means one connector, one row. Here's what it looks like. If I wanted a two-row connector, I could do something like that. All kinds of cool connectors in here. But for our power and ground, let's just use these little connectors here. They're good enough. So I will put one over here. And boy, I know that, let's look at our connector. Here it's showing the connector here and the electrical connection here. And that's really not the way we want it. We know it's going to kind of come out this way. So what I'd really like is the connector shown here and the wire here. So let's go back into KiCad. And what I'm going to do is I'm going to press M on the keyboard. That allows me to move it. While I'm moving it, I'm going to rotate it. R, no, there we go. That's the way I want it. So that's looking pretty good. And let's say that that'll be the one for the battery. Let's make the one for the ground. So for our ground connector, I'm going to just go over here and press C on the keyboard. And we'll just put it kind of over here. I could put my ground down here, but then it would not really show that power and ground are right next to each other like they'll be on the schematic. So I'm going to just put it over here for now. Now, let's do this one here. So here, instead of using two single connectors, I'm going to use a double, and it'll make it look more like what I have here. So we'll go over and we will pick, we'll go back to connectors, generic, and looky here, 1 by 2. Well, that looks pretty good because it kind of shows that they're right next to each other. So that's a useful thing. So I'll hit OK, and I can see my part that I just picked, and I know I'm going to want to rotate it to make it match the schematic that I'm trying to do. So instead of selecting it, placing it, and then moving and rotating it, I can rotate it right here. So I'll just hit R, R again, R a third time. That's looking pretty good. So now I have my connectors in place. So I've cleaned the schematic up a little bit. All I did is just move things around and rotate things. For example, you can see I rotated these two resistors that used to be going up and down. But I kind of spread things out, but I also put things in line with each other. You can see that these are all in a line. These are in a line, so we'll have a nice straight wires going down. These are all in a line. These are on top of each other. And my grid is really helpful because when I'm moving these components around, for example, let's go over here. I'm just going to zoom in. See how my grid is showing me that these are actually lined up? And remember, you turn the grid on and off with these dots here. No grid. Why would anyone in their right mind want to do that? Grid. So I used that grid quite a bit as I was moving things. Where did I put these resistors? Easy. I put them such that I can get my wires out of these comparators. See that? So I kind of knew where these needed to go. You might notice that these are in a line because now my wire is going to come from the battery. It's going to go up here, it's going to go down here, and then it's going to go through. And you might notice that I put these in a line because I just want to drop a nice straight wire down to this variable resistor. And I also kind of put this variable resistor where it's easy to see because this is kind of the gizmo that's making this thing do its stuff. You change this resistor and it's going to change the lights. So I may not have got this exactly right, but I think it's pretty close. So I'm comfortable drawing some wires now. So here we go. Our wiring tool is this green guy here. The blue one is for placing a bus of multiple wires. You comp's may end up doing that if you lay out a microprocessor board. Here's another nice bus tool, but we don't need a bus on this design, so we're just going to use the green wire. So what we'll do, I'm going to zoom in a little bit, and I have the tool selected. I'm going to come right in here. I'm going to click, and I get a green wire. And I'm going to click again. Over here, I'm going to click, and I'm going to click again. And the reason this is working so nicely for me is that everything is on the grid. So let's move down. And I should also point out that I like to use the zoom wheel to move around on these, but I can also use Shift roll goes up and down, and Control roll goes left to right. And I use those two. So let's draw another wire. I've got my wire tool, so I'll go over here and I'll click. Click again. Even I can do this. Click, click again. Let's zoom out. Let's do these ones because they're kind of fun. I'll zoom in. I'll say, come in from the battery. And look at this, I just move my mouse up, and it's taking care of my right angle for me. And there I go. I've made the connection. Did I really make the connection? Take a close look right here. I did not. This connection wasn't made. Kind of looks like it is, but it's not. So I can do a couple of things. One thing I can do is just draw another wire, and everybody's happy. And if I go to my select tool, I actually have multiple pieces of wire here. Let's see if I can get that. Okay, maybe I'm not able to do that. But the other thing I could have done is gone up here and just hit the delete key. Said, I don't want that wire anymore, and I don't want that wire anymore. Gone back to my wire tool and been a little more careful. This time I'll go all the way inside there and I'll get a nice connection. Now I'll use my Control scroll to move this way, and let's put in this wire. Go like that. This one's so easy, let's just do it. How are we doing? Looking pretty good. Let's do these. So I'll zoom in a little bit, go right inside there, and put it in there. There. Again, what I'm doing, I lay it in the circle, I left click. I drag my mouse down, I right click. So now I'll do a little bit more, and then we'll come back in just a second. So now you can see that I have put in most of the rest of the connections. But a big connection that you don't see here is ground. Got one here, 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 here where the power comes in. So let's put that in now. So what I'm going to do is I'm going to place a component, and if I wanted, I could use this little power port symbol here. That works fine, but I'm going to do it by just placing the component. And I'm going to do a search on GND. And looks like I've got some options. I have ground. That looks pretty good. Ground 1, ground 2, ground 3. And the reason that there are different grounds shown here is some schematics, when they get pretty complex, they can have different grounds. They can have analog ground, that's GNDA, digital ground for GNDD, all kinds of different grounds. Earth, you got the nice earth symbol there, a different earth symbol, all kinds of cool stuff. But we're just going to use a basic, simple little ground symbol. And I am going to need one down here. So what I'm going to do is when I place it, I'm going to make sure that it's nicely in line. So I'm going to zoom in enough so that I can see the grid here. And I'll just put it right there. And I know I'm going to need another ground here, so I'm going to be lazy and just copy this one with my C from the keyboard. I'll zoom in, go up a little bit by shift roll, make sure I'm on the same grid so I can do a straight line. I'm just making it easier for myself. And then our second to the last ground is going to be our power input here. So let's do the same trick. We'll do a C, and I'll zoom out, zoom in, and I'm actually going to put it out a little ways because that's just going to make my schematic look better. Instead of crunching them up together like that, I'll put it right here. So I think that'll look better. The eye does not like to see things all crunched together or too spread apart. That's just irritating. And part of what we're doing is really making art. A person who is really good at making schematics will make schematics that are just easy to read. They're beautiful. I do not make beautiful schematics. I make okay schematics at best. But let's see how I can make this one a little better. I know I need to put a ground right over here because this is my V- terminal for the comparator. And that ground is going to kind of get in the way of this text. So what can I do? Well, it looks to me like I could just move this text down below the component, maybe put this one. Actually, I can just move this text up here and I'll have plenty of room for the ground symbol. So let's do that. So I'll go over here and say, and hit M, just kind of move that. Actually, no, that's not near the component where it needs to be. We want to move things down a little bit. Let's go like this. I was originally going to put this down below the components, but you know, this works. Let's kind of put them all in the same place because that way, when you look at these components on the schematic, oops, move that, their reference designator and component types will be kind of in the same place, and that just makes it easier to read. Like that. There, that looks nice. And see, now I have a clean place to put my ground. So I'm going to put my ground. I'll just copy this one here. I hit the C key. And, you know, let's actually just butt it right in here. So I'm going to put that right on top there. And there's my ground symbol. And, you know, just to keep these from being too close together, let's move M, this, kind of put it over here where it's out of the way. Okay, so now let's connect those grounds. So I'll zoom in here, get my wire over here, and go like that. That's one. Let's do this one. I'll zoom in and it centers. And it'll make the right angle for me. So that was nice of it. Do I have any more? Yeah, I have one more. Okay, we're looking pretty good. But we're still missing something. We are missing our 9-volt connection up here. Because remember, this goes to 9 volts. We're going to power our component from 9 volts. And let's actually go back and look at our schematic. Our 9 volts is going to come from here. So what we want to do is we want to be able to make these little arrows that will point to things. So let's go back to our schematic. Looks like we already connected our pot to 9 volts, but we have to do these. And here's what we're going to use. The reason, if I wanted, I could just make a wire that went from here over to here and then right in here. But I want you to learn how to make net labels. It's really easy and it's really cool. So what we're going to do, we're going to go over here and we're going to go to Place Net Label. And I'm going to drop it down. Actually, when I click, it's going to ask me what it wants me to say. And I'm going to just say 9 volts. And for those of you that are compies, it's just like a variable name. The schematic now knows what this name is, and I'm going to put it right on top here. That says that goes to 9 volts. Does the schematic know what 9 volts is? Absolutely not. That's just a label. So now what I'm going to do, I'll go back to my selection tool. Let's hit C. Make a copy of this. We're going to shove it right there. And now let's make a copy here. And C. And I know, whoops, it's not pushing over. So what I'm going to do is just scroll my way out. And I really want that to be right here. But you know, when we look at that, let's actually do it. I put that there and I go, oh, 9 volts, 9 volts. Boy, it's kind of hard to see 9 volts here. I need to do better than that. So I want that 9 volts to come out up here. So what I'm going to do is just move this piece of text. So M, and put it up here. And at the same time, let's move this reference designator over here. So now I've freed up some room. So let's move our net label for now. We'll move it kind of up here. And we'll get our wiring tool. And we'll just go boink. And then we'll come out like this. And I'll like double click. And now I'm going to take this 9 volts and put it on there. M, put those squares on each other, and I'm in good shape. Now you can see that this is where our 9 volts comes from. And then the schematic is going to make sure to put, to connect all these together when it makes what we call the net list. So our schematic is starting to look dangerously good here. There are a couple of little things I don't like still. We don't want to have too much information on the schematic. We want everything you need and nothing you don't. And this looks pretty good. I got reference designators, I got component types, I've got my grounds, my 9 volts. Here's some superfluous information. I don't really care that this is a connector 1x2 right here, nor do I care that this is a connector 1x1. So I'm going to double click and I can see a value for the connector. And I'm going to go, don't show me that. And it's gone. Let's do the same here. I don't want to see that. And let's go over here and don't show this. So now our schematic is very close. There's one more thing we need to do, and that is assign what KiCad calls power flags. Okay, now we're going to do something that is a little bit tricky to understand. So I want to give you a little detail on this. So when I mentioned before that what we're doing is drawing a schematic. We're not drawing a schematic that's going to go into a simulator. We're drawing a schematic just to show things how things are connected. But KiCad and any other CAD program, they're pretty smart and they do design rule checking. So, for example, the pins on this IC actually have attributes. These are inputs. This is an output. And schematic capture programs, if you connect two outputs together, they will give you a design rule violation. And so we have to be a little bit careful. And the thing we're going to do right now is we're going to tell KiCad where power is, because it expects, the design rule checker is going to expect this connection to come from something that is flagged as power. And the way we do that in KiCad is we use what's called a power port. So what we're going to do is we're going to go to place symbol, we'll click, and we're going to go to power. We go down here and we're going to find power flag. Let's look at the definition. Power flag is a special symbol for telling ERC, which I believe is the design rule checker, where power comes from. So we need this little thing on our schematic. So we're going to say, give us one, and we're going to put it right up here on 9 volts. And that's going to tell the design rule checker that this is power. And you can see it goes over to here, goes right in here, and everything should be happy. So let's do a couple more things. Let's label these so we know what to do with them. Or in other words, we've got these connectors just hanging out here, but really our schematic should say what they did. I mean, even I did that. I wrote battery 9 volts, ground. So what we're going to do is we're going to just put some text in our schematic. So I believe that there should, normally, I'm used to seeing a little text icon down here, but I can't make it work for some reason. So what I'm going to do is go to the menu and say place, graphic text. All this is a piece of text to make humans happy. So I'll click. What do I want to say? I want to say battery. Let's use all caps. Then it'll look more official. 9 volts. And look, I can make the text size whatever I want. I can make it bold, italic. Let's see how it looks. That's too small for my schematic. So I want that to be bigger, because as you look at the schematic, I really want battery to be called out. So I'm going to double click it. It says text size is 050. Let's double it. That's inches, so let's make it a 10.1. Looks a little better. Let's move it over a bit. Whoops. Move. Looks good, but I still want it to stand out. Double click it. Let's make it bold. I love it. Now you know what that battery's doing. And let's also flag ground here. So instead of going through all that formatting, let's just copy this. So I'll go C, bring it down here, double click it, and say ground. And let's take another look at things. Look at all my resistors I've got. Everything is kind of in good places here, except for this one. That's kind of weird, isn't it? Look at that. Let's move these labels so that they're kind of where the other labels are. So I'll click here and I'll say move. And look, it's given me a little line showing which component it's associated with. I want it up here, but I'm going to rotate it. So I'm going to hit R. Put it right down there. Kind of in line with that one. Same here. M, R. Okay, now I want to show you one more little trick of KiCad. And remember we said that this text was going to be 1/10 of an inch high. And there's a nice way of measuring things in KiCad. What you do is I'm going to put my cursor right here, and I'm going to hit the space bar. And do you see this dx, dy? Hitting the space bar zeroes that. So if I put my space bar here, I put my cursor here, and watch this while I hit the space bar, it zeroes it out. I look up here, and dy is about 1/10 of an inch. It's actually -1/10, just the way they specify that in KiCad. And you can see that this writing is about 1/10 of an inch high. So that is really going to be useful when you're doing your PC boards. Okay, so we have a schematic, and it's looking pretty good. So now we are ready to move on to the next step. So with our schematic complete, we now know all the components we're going to use. But you notice we've put in their values, but all the reference designators are just question marks at this point. RV question mark, R question mark, U question mark A. So what we're going to do now is we're going to annotate the schematic, meaning we're going to assign reference designators. To do that, we go up here to this tool that says Annotate Schematic Symbols. So I click on this, and I'm going to get a couple of options. First of all, if I have a multi-page schematic, I can either re-annotate the whole schematic or just the current page. I can keep existing annotations. Like, for example, if you're working on your senior project and you just change one component and you don't want all the annotations to change because you've been referring to R1 and R7 in your progress reports, you might keep existing annotations. Another one is reset the annotation, but keep the order of multi-unit parts. Remember, multi-unit parts are these guys here. You can also tell it which way you want to annotate. Or in other words, which way should the designators increase? Should they go down and then up and then down, or over and to the left and down? I usually do it by X position. You can start at whatever number you want. Like a lot of things in KiCad, the default menu is really good. So I'm going to hit the button here for Annotate. And KiCad always tells you everything it does. Doesn't seem to be complaining, so we're going to close and check this out. Connectors, J1, J2, J3. Here's R1. Here's R2, R3, R4, R5, R6. RIC here ended up as U1. That's no surprise. So now our schematic is annotated. So now what let's do is let's use the design rule checker. So what we're going to do now is we're going to ask KiCad to look at this, and it's going to make sure that we don't have two outputs connected together, or we don't have two inputs connected with no output driving them. It's going to catch things like if we have an unconnected, what we call net. Like if we have a wire that just goes off and doesn't go anywhere, it's going to catch stuff. So let's see how we did. So I'm going to hit the bug, and I'm going to run it. And let's see. We have pin is connected to other pins, but not driven by any pin. So pin 12, the power input of U1, is not driven. Let's take a look. So pin 12 is coming from ground. So what I didn't do is tell the design rule checker that ground is actually a power connection. So my ground needs a power flag. So let's fix that. How do we want to do it? We could just tack a power flag on any of these grounds, but that won't look as nice as if we just do it as its own little power flag. And look at our schematic. It's kind of lonely down here anyway. I'm going to put my power flag and ground over here because I don't want it to compete visually with this, but I do want it to be by I want it to sit by itself. So here's what we'll do. First of all, let's copy the ground symbol. So I'll go C, and we'll just put that over here. I'm certainly not going to put it down here because you'd never see it. So I'm going to put it up here where we can find it. So how about right about here? And then I'm going to draw a little wire like this. And look, it's trying to put my right angle in the wrong place. So, hey, look, I didn't actually connect it to the ground symbol. So I'm going to hit escape to say, forget about that one. Let's go back to our wire tool. We'll go right in the center of that dot. Go over here. I'm going to double click. And you can see that little hollow square is telling me that I've got a line that's kind of hung out in the middle of nowhere. Let's go up and steal our power flag off here. I'm going to go to the select tool, and we're just going to copy this. Let's see. Why won't it let us copy our power flag? Oh, because I had my mouse over the text, not over the flag. So we'll take that and we'll put it right here. And that kind of tells us that ground has a power flag, though really this is for the design rule checker. Let's see how we did. Save my work, so I'm up here. And we'll go back to the design rule checker and say run. And look, we got a clean report. But we're not done with this thing. Let's have a little fun with it. What we'll do is let's pick on this connection right here. I'm going to hover on it and I'm going to hit delete. Now what I'm going to do is I'm going to draw my connection, so I'm going to start drawing, and then I'm going to mouse wheel out, and I'm going to get real close, but not close enough. And schematic looks good, right? Let's go to our design rule checker now. Run, and it says you got a problem. So that's kind of cool. So it's telling me exactly where the problem is. I can look at it by either where it is in inches in XY coordinates, or I can just look at what pin it is. So it actually gave me a little arrow to say that this pin wasn't happy. So what let's do is let's just hover over here. We'll delete this. We'll get our wire tool. And I'm not going to start here because if I did, I'd have to follow the grid and know where to start. So I'm going to start over here because it's easier. I'm going to go over here and double click. And now I'll save my work. I'll go back to the design rule check. And we have no errors in this schematic. So that means we're ready to go on to the next step. So now we have a good schematic and we're ready to get started making our PC board. So our schematic tells us how everything connects together on this board, but it doesn't tell anything about the physical size of any of these components. So what we need to do now is we need to tell this program what packages these components are in. For example, these could be surface mount resistors, or they could be through-hole resistors. These could be 5-watt resistors that have a huge footprint. They could be, quarter-watt resistors that have a small footprint. This could be in an SOIC, a small outline integrated circuit package, or it could be in a through-hole DIP or dual inline package. And so what we need to do is we need to make an association between these schematic symbols and their footprints. So what we'd use for that is we go up to this tool up here, and this allows us to assign PCB footprints to schematic symbols. And we do this after we're happy with our schematic, though it's easy to go back and add things to our schematic later on and go through the process again. And we actually will maybe even do that as we go through this tutorial. So let's click on this. And what I'm going to see is here are all the goodies that are on our schematic. You can see all of our components, but there are no footprints assigned. So what let's do is let's start off with our resistors, because those are pretty easy. And also, let me mention that for this schematic, we're going to use through-hole components, just because they're easier to work with. You're free to use surface mount components. They're a little harder to work with, but it's the way industry has gone. So in industry, you'll work with surface mount. But we want to keep things easy to solder, so we're going to go through hole. So here's what I'm going to do. I'm going to go over and select R1, and I'm going to go through the list of all the footprints I have. Look at all these cool footprints that come with KiCad. In addition to the footprints that you get that come with KiCad, if you go to DigiKey and buy parts, they frequently will include a downloadable footprint for those parts. So if you use some part that's different than what we have here, and you want to use it in your PC board, your options are you can download the footprint from DigiKey and use it, or you can make your own footprints with the footprint editor. We're not going to go through that in this example because we don't need to, but for some of the parts on my guitar amplifier, and here's my newest board, by the way, I'm very proud of it, I've had to make my own footprints, and it's nice because I get exactly what I want on the PC board. But our problem right now is R1. So let's go find ourselves a footprint. I'm going to move this over. You'll see why in a bit. We'll go down here. Look at all this cool stuff. Doesn't that get you going creatively? So I see resistor SMD, or resistor surface mount device. And then I see resistor through hole, THT. Let's go to THT. So When I click that over here, I see all my options for resistors. And something that's good to remember is that 1 inch is 25.4 millimeters. So I can use that to kind of put things into inches. Let's look at our possibilities on these resistors. Come on. Array? Nah, we're not an array. We're not a single inline package. We're not that. Looks like we're going to have a vertical here. That's not us. Axial, now we're talking. So length 3.6 millimeters. That's going to be pretty small. My through-hole resistors, I just happen to know that they're about 4/10 of an inch. So I'll take my calculator and say 0.4 inches times 25.4 millimeters. I'm looking for somewhere around 10.16 millimeters. So let's go down here. I want an axial. That means that the part lays down like this on the board. A radial part goes up like that and it has its leads coming down, but an axial goes like that. So I go down through my list and I see, let's see, an axial. Let's see, how about this one? Now, what does this part look like? Let's go to the footprint viewer. So from here, I'm going to go up here and just take a look at this part. So it's allowing me to take a peek at it. And I kind of know what I want, but let's measure it to make sure. What I'm going to do is I'm going to put my cursor right here and I'm going to hit the space bar and that's going to reset my XY coordinates. I'll go from here to here and I can see that DX, looking down here when I'm over up here, is about 0.393 inches, and I'm in inches. So I'm liking that. What I should also do is check the hole size compared to my leads, but I know that this one is correct. So I'm going to go ahead and just use it. So we'll move this out of the way, and I'll say for R1, give me this guy here. And I'll say, bing. And now you can see that R1 has been associated with this part. Let's do the rest of our resistors. I'll just double click my way down here. And okay, and so now my resistors have been assigned. Let's do our LM339. Now for this part, I know that I want to use a dual inline package part through hole. So I'm not going to look up an LM339 in this list here, because just like my schematic doesn't care about packages, my packages don't care about the values. So what I want is just a package that is a dual inline package. And LM339, let's make sure we know how many pins it has. Let's see. 3, 6, 9, 12, and then power and ground. So it's 14 pins. So we'll go back. I need a dip 14 part. So let's just go hunting here. We can also search up here, but I'm going to just hunt. One of the things I like about hunting is it just shows me all the cool stuff that's in here. Doctor. Package. This looks good. Package, dip, dual inline package. So let's see what we got. Look at all this good stuff. Here's a dip 4-pin. We don't want that. We want dips 14 pins. So let's go up here. Dip 14. Okay. And I know that dip packages are 3/10 of an inch. And 7.62 millimeters is about a third of 25.4. You should always check this stuff very carefully. I kind of know it off the top of my head because I've done it a lot. So I'm looking at this package here, and it's got a 7.62 width, and I see long pads. What long pads means, let's just take a look at it. We'll go to the component viewer, and you can see that these pads are pretty big. So it's going to make it easier to solder. Now, take a look at the component outline. When we do our design rule check with our PC board, we better not put anything inside this outline, or the courtyard as they call it, otherwise we'll get a design rule error. Now for this part here, it is intended to not have a socket. So that means that the courtyard will be a little bit smaller than if it did have a socket. So let's keep looking. So let's see, 7.62, hey, look at this, 7.62 millimeter socket long pads. Let's see if we get a bigger courtyard. I'm not sure I see a bigger courtyard, but let's go back and look just to. They actually look about the same. But I'm going to use this one because there may be something that I don't see there. So I'm going to go ahead and use this. Why a socket? Because if you solder that IC in and then you blow it up, you're going to have to unsolder 14 pins. Or if you make a mistake, you're going to have to be cutting traces, where if you put the part in a socket, you may be able to just pull it out and put wires on it. So if I'm prototyping, I'll often use a socket. So let's use this. Okay, so now we've got those parts in. Next, let's assign our LEDs. So what I'm going to do is I will select my LED, and then I'm going to go hunting. And let's see what we can find. LED surface mount, LED through hole. That's us. So this kind of shows us what our options are. And we have quite a few of them. And I just want to get something really simple. So let's just take a look through here at what they kind of look like. We're going to use the footprint viewer. Remember, we got there from this icon up here on the upper left. Let's just see what some of these look like. Not that. Nah. Let's keep looking. It's not bad. 3 millimeters. Let's see what else we see. Okay, so 3 millimeters, that looks like a pretty good size. That's going to be about 1/10 of an inch. 1/10 of an inch would be 2.54 millimeters. So I think this one will work for us. And you can see it's got a square lead on it. So of course that's going to be the cathode, which is industry standard. So now we've picked the one we want. It's number 14 here. And we'll say that goes there. I'm just double clicking these. Okay, so now we have our LEDs assigned. Now let's assign our connectors. Now you remember that we had 2 connectors that were just 1 pin, and then we had one that is 2 pins. Going back to our schematic, this is our 2-pin connector. And for it, we want these to be 1/10 of an inch apart, and there'll be little pins that come up, and then we're going to put a shorting plug on them. For these, we're going to want to use wire pads so we can solder a wire. So let's get this one first. So for our connector, we're going to have to find a footprint that has 1/10 inch spacing, because that's what the little pins that you've seen in our labs are. And so let's go take a look for that. So this actually took a little bit of looking, but what I'm looking for is what's called a pin header, because there are a bunch of pins that stick up. In this case, we just have 2, but it's a header. It goes down on the board. That's the industry standard term. So let's look for connector pin headers. Here we go, connector pin headers. And I know that I'm 1/10 of an inch. And since an inch is 25.4 millimeters, I know I'm 2.54 millimeters. So here we go, connector pin header 2.5 millimeters. So that's 1/10 of an inch. Okay, so here are our choices. So let's see, 1 by 1, no, that's just 1 pin. Ooh, 1 pin by 2, that's us. Horizontal, let's take a look at that. Horizontal means that it's laid down on its side. It's mounted horizontally. We don't want that. We want 1 by 2 vertical. That looks pretty good. And what let's do, just to make sure, is I'm going to put my grid in inches, and I'm going to hit my space bar to 0 my dx and dy. I'm going to go down here, and my grid is actually in millimeters. So let's change the grid here to, let's see. Let's change our grid to 25 mils, which means 25 thousandths of an inch. Again, I reset my grid, I look down here, and if you look at the dy down at the lower right-hand side, you'll see I'm 1/10 of an inch. So see, I can measure my components. If I want, I can zoom in. I can actually measure the hole on this thing. So this component viewer is really cool. It's really neat. So we will go to our 1 by 2 here. And this is our connector we want. Whoops. Let's make sure we did this right. Connector pin header 2.5 millimeters. Looks good. Now let's put down the footprints for our power and ground connectors. So these are going to be wire pads. And so if I look down through my list of possible connectors here, I go down here and I see connector wire. And the pads that I'm finding they all have square pads. Here's a 1 by 1, it's a square pad, and it's really pretty small. Even if I get up here, oh, yikes. We want a 1 by 1. Bottom line, I go through these and I'm not seeing what I want. So what I'm going to do is I'm going to go into my own library and use a wire pad that I made for myself. Now you can find these out there on the internet. You may be able to find it from DigiKey. But I have my own little footprint library that I creatively call Footprint. It's right here, and here are just a few little gizmos that I've been using for the 430 lab for my guitar amplifier. But here's my solder pad that I really like, and so I'm going to select it for both of these. So in your case, you will have to go find a wire pad that you like out on the internet, and that'll be a little bit of work for you, but it'll give you some experience getting footprints. So the last component we want a footprint for is our variable resistor, or our potentiometer. This is one of the trickiest parts of a schematic like this, because when you have a potentiometer, you want to make sure that you wire it correctly. What I will often do is I will write CW on the side of the potentiometer where the wiper goes when it's fully clockwise. In fact, I think we can actually just do this. Let's put some text in here, and I'm just going to say CW on my schematic. I do this on all my schematics because what this tells me is that if I turn the potentiometer fully clockwise, pin 2 is going to be connected to pin 1. So when I pick my footprint, I need to make sure that that is indeed what that potentiometer actually does. So let's take a look at our potentiometers. Here it is. It's the one piece we haven't done yet. And so what we'll do here is go through and we'll find potentiometer through hole. And here's a good tip for using KiCad. Look at these part numbers. These Burns potentiometers, you're actually using the part from the manufacturer. And so you know that it's going to come out right. So let's just pick this 3266. It's a horizontal part, and you can see in the footprint, it shows that it's going to lay down on the board like this, and here are the pins. Here's the little adjustment thingamajiggy. If we want, we can use the same thing as a vertical. So now it's showing that the adjustment is up at the top. Let's use this one. So I will double click on it. And did I check my pins? Oops, wrong thing. When we looked at our potentiometer, I didn't check pins 1, 2, and 3. Now, if I want, I can look into the symbol and see which one is 1, 2, or 3. But what I actually like to do is lay it down on the PC board and see what it looks like. That way I can really check it. And you'll see how to do that in a bit. Okay, so at this point, it looks like we have finished all of our component associations. All these components in our schematic are associated with footprints. So what I'm going to do is say OK. And at this point, I can make a netlist. And what a netlist is it's a file that contains all the schematic connection information, and it's going to contain the footprint associations. So I'll go up here and say generate netlist, and I'll use the defaults. Give me a netlist. It's going to put it right in my directory. I appreciate that. And I'm going to save it. So at this point, we have completed our schematic. We're ready to design a PC board. So what we'll do for our PC board is we will go back to the main KiCad project screen, which means we'll go back here. We've done our schematic. Let's go to the PC board. So it's giving me a blank here. And what I'm going to do is I'm going to load the netlist from the PC board. So I'm going to go up here to the netlist tool. And looks like I have to give it the file. So let's take a look. KiCad tutorial with a file extension of net. And KiCad's very good about telling you everything it does. If there are errors, it'll tell you. So update the PCB, close, and look what I have. Here are all my parts. It doesn't know where to put them. So it just kind of threw them out there. So what I'll do is I'll zoom in, and what I'm going to do is I'm just going to separate them first of all. So actually, I won't do that. What I'm going to do is I'm going to kind of place them very roughly where they belong on my PC board. So what I do, I click to deselect everything, and I'll say move. And I'll put this over here. And then I'm going to look at my schematic, and I'm going to place everything roughly where it needs to be. And I'm doing it just with the move where I hit M. Whoops, that just moved the field. Here, I will move the component. I can rotate it if I want, but I'm just going to kind of throw things roughly where they need to be. So what I'm doing is I have some good music on, and I'm just unscrambling that mess that we were given. And so I've worked on it a little bit. I'm just moving parts and rotating them. What you can see here is I have what's called the rat's nest. And the rat's nest gives you straight connections. They'll cross over each other. They're all just straight lines. But it's really useful because it kind of tells you how things are hooked up. I can turn the rat's nest on or off. On is obviously where I like to have it at this stage, because if the parts are in about the right places, your rat's nest will really look pretty simple. So you can see that what I've done here is I've kind of made our schematic look, our PC board look kind of like the schematic. Here are our wire pads where our plus and minus are going to come in. I kind of knew to put this one, see, I can click it and I can move it. I know that this is going to be my positive one because I see the rat's nest line going into my little jumper. So I kind of know it's in about the right place. And the other one, I can see the ground going to a bunch of different places. So it's pretty clear that this is the negative. So I'll throw it here. Here's our line of resistors for our voltage divider. And let's zoom in with that wheel. And you can see I kind of put them about where they're supposed to go. Here are our LEDs. If I want to move them, I can move them individually by selecting them like that. Or I can say, let's move them all. And I'll select them all and hit move, and I can move them all. And you can see that I put these resistors so they're next to the right LED, but I didn't rotate them correctly. So I'll come over here, select the component, and if I want, I can just rotate it, but it's kind of rotating with one foot nailed down. So what I usually do is I hit M for move, and then I rotate it and move it at the same time, and I kind of come like that. So I got a nice straight line. Let's do the same thing with this one. M. Now I can move R. Kind of put it like that. Just kind of lining things up a little bit. M, R, M, R. I'm just kind of iteratively moving where I want to be. Looks like I got to move this over a little bit. So now I can see that the connections to the LED have the shortest length, and I can see that 9-volt connection up here. So I've got a little more work to do. What I'm going to do now is I'm going to really kind of zero this thing down and kind of crunch things together, and I'm going to get a feel for how big my board really needs to be. Now, this is a bit artificial because we're going to make this board as big as it needs to be. Typically, you will have a constraint. Like for my guitar amplifier board, I know exactly how big it has to be to go in the case. And I also know where the guitar input and the auxiliary input, I know where those have to be on the board to make it fit together mechanically. So when I design this board, I start off with my board outline and my connectors, and then I make all the electronics fit. But you guys are just getting started. So what we're going to do is we're going to kind of put everything where it needs to be, and then we're going to dimension the board around that. I've made some more progress with my board. So you can see my rat's nest is getting a little bit cleaner. And I want to show you, you want to set your grid when you design a board. And this is the grid right here. And if I use a really small grid spacing, then I can place things very, very close together. A larger grid spacing means things will only snap to, in this case, points 50 mils apart. You might say, well, I should use the smallest grid spacing possible. But if you do that, it's a little harder to make all your parts line up. On the other hand, if you make your grid spacing too large, then you won't be able to put components closely together. For a simple board like this, I'll use about 50 mils, which is 50 thousandths of an inch grid spacing. And in my case, I just prefer working in inches. If I want, I could work in millimeters, but I prefer to work in inches. So when I'm in inches, all my numbers down here will come out in inches. It can be frustrating if you change your grid spacing partway through your design, because traces and pins that are not on the grid, the program won't allow you to connect to them. So you want to get your grid down right when you start. A couple other things I notice. I see a lot of stuff in here. I'm seeing component values. I see all this silver stuff. And that's kind of in my way. The blue stuff, the R9, the D2, those are going to be on what we call the silk screen of the board. So I want to see those, but I don't really need to see this other stuff. So let's go over to our layers window on the side here, and it's picking what to show us. And here's the front copper. This will show us our traces. Yeah, we want that. Back copper, we need that. We're not doing surface mount, so let's just turn this layer off. The paste layer, that's surface mount. Let's turn that off. Front silk screen, yeah, we want that. Watch what happens to the blue when I unclick this, the blue text. See how it goes away? Well, I want that silk screen right on the board. The silk screen is the little white markings that you probably can't see here, but they show where R1 and R2 and stuff are. So I want to see my silk screen on the front. I'm not going to put a back silk screen, so I'm just going to turn that off. My solder mask layer, I don't need to see that. The back mask, I don't need to see that. These other things, I can leave. My margins, that's not the one I was looking for. Front courtyard, let's look at that one. Front courtyard is showing me the area that these components want to take up. Like, for example, let's say I move this LED, select it, M, I move it over here so the two courtyards overlap. I'll get a design rule violation when I look at that later. So I want my courtyards to show up here because I want to know where they are. The fabrication, that layer is something that the program will make for you that allow the people who are stuffing the board to work with it easier. And look what happens when I enable and disable that. I get rid of the values, which I already have. I get rid of the values, which I don't need to see, and I get rid of the description. So I'm just going to get rid of that because it's just complicating things for me. And there's nothing on the back, so I'll disable that. So now things are a lot clearer. And I can kind of see where things go, and I can kind of see where my routing is going to go. Let's see if I like it. Okay, I put these resistors in kind of a nice little line. These are our voltage divider. Those are good. Do I see a lot of lines crossing around our LM339? Yeah, I see some. Let's say that I can, there are too many crossing lines, and I say, you know, if I just reassigned the pins of that LM339, I could get a lot of these lines to not cross, and I'd have a cleaner layout. So if that were the case, I'd go back to my schematic and I'd just move these parts around. I'd just exchange them. And then I'd make a new net list, and then I would read that net list in, and my rat's nest would be cleaner. And I could do that on this schematic, but it's not really necessary. But like, like the way designs typically go, I can see some things I'm missing. One thing I'm missing is I didn't put any mounting holes on this. So my printed circuit board is just going to be a board, but I'm not going to have any mounting holes to secure it to anything. So I got to go back and fix that. The other thing is I don't have a filter capacitor. And on any design like this, you of course have filter capacitors in the power supply that's driving it, but we're going to go down through the wires into this board. I want to bypass that power supply right on the board. So oops, missed a component. So let's go back and fix that. So I'm going to save my work here because I don't want to throw this away. And let's go back to our schematic program and let's see what we want to do. The first thing I want to do is I want to put a filter capacitor on this thing. And do I want it here? I'm going to use an electrolytic capacitor. Shall I connect it here or here? Which side of my connector do I want to put it on? I have to go back to experience here. Electrolytic capacitors have a slight amount of leakage. So I don't want to put it right here, because when this thing is sitting in your backpack and you have this connector disconnected, it's going to slightly discharge your battery. So I want that filter capacitor to be over here. So what I'm going to do out of laziness more than anything else is I'm just going to slap it on right here. So what do? I go back to place component, and it's going to be here. So I'll click here, and let's look at our components. You'd think they'd have one for capacitor, but they don't. So let's go to device, which is kind of our catch-all, and CP, polarized capacitor, the way US likes to see them. So that would be this one. And yeah, that looks pretty good. Let's look at some of the others. Europeans like them that way. Here's a smaller one. I don't want that. I like this one. Looks like the kind of capacitor we'd see in one of our textbooks. And it's marked with the plus and the minus, and it has the little curved guy on the bottom here telling us this is a polarized capacitor. And our experience tells us that capacitor is going to leak, and that's why we want it on this side of our power connection. So we'll just slap it in here somewhere, and let's connect it up. I'll zoom in a little bit and go to my wire drawing tool, go right in the center of that little dot, and connect that over here. And now let's give it a ground, and I'm just going to steal a ground here. I'll hit C for copy, put those things right in line, and connect them up. And let's give it a value while we're at it. We're going to use a 10 microfarad. So we'll go in here and double click. Oh, sorry, that's the reference field. Don't want that. I want the value field. And I'm going to say 10 microfarads. And remember that 10 microfarads, that's just to keep me happy here. I could have written 10 coconuts if I wanted, and the schematic would be happy. Now what I'm going to do is the mounting holes. Before we do that, let's talk about those mounting holes. I want my mounting holes to connect to ground. So they're actually going to be part of my schematic. Why do I want to mount them to ground? Because typically the frame of your device is going to be grounded. Not all the time, but usually. So if that's the case, my schematic needs to know about those mounting holes. So let's go hunting and see if we can find some mounting holes. Finding the mounting hole is easier said than done, but let's go take a look. So we know we need a schematic component. We're going to put it somewhere down here. And where we're going to go is to mechanical. Let's see, let's close this. We're going to go down here to mechanical. How do I know that? Easy, because I stopped the tape and hunted for it. And it's not easy, but I go down here and I see mounting hole without connection. Here it is. That's a mounting hole that is isolated from everything on the schematic, but I want our mounting holes to be grounded. So I'm going to say mounting hole pad with connection, and I'm going to say, give me one of those. And as long as we have it here, let's put it roughly where we want it. I'm going to put it somewhere over here, maybe. I'm not going to put it as far out as these because I want the eye to see these first. Where I really want it is right about here. So I'm going to kind of put it there for now. And now what let's do, let's move this power flag over here. Just kind of set it out of the way for now. And we want to have 4 mounting holes on the board. So let's copy this and get some more. But before I do it, I'm going to rotate it. So move, rotate, not that way. Rotate, rotate. That's good. Now I can connect this thing to ground. So I'll just put one here. Let's zoom out a little bit and let's get 4. Actually, before we do that, let's get rid of this mounting hole pad text right here. We don't need that. Mounting hole pad, show, we don't want to show it. Okay, and let's see, here we have H, looks like it's got a reference designator. Let's move that reference designator a little closer. Move it maybe over here. Actually, let's move it over here because that way we can put these closer together. You'll see how in a bit. Copy, C, and notice how I'm putting these right on the piece of grid I see here, which looks about right. C. Right on that grid. Looks like I didn't get this one quite right. Now we're looking good. C, put that on that grid. There we go. Now I want all these to go to ground. So what let's do is let's actually take advantage of this. I'm going to just move this out of the way a little bit. And let's put our mounting holes kind of up here. Because we want them to be visible on our schematic, but we don't want them to grab your eyes because that just makes our schematic harder to read. So let's take our ground symbol, and I'm actually just going to move it. And I'm going to put it right here. And let's put our power flag over. Let's put it here. You can see that I'm being careful to go right onto the grid because the grid is going to assure me that everything's lined up. So I no longer need this line anymore. So I'll just put my cursor over it and hit delete, and it's out of there. Let's connect up our mounting holes. that. And then let's go like this. What the heck? Let's go like this. Beautiful. Our mounting holes are going to ground. Let's take a look at our schematic, make sure we like it. Okay, we've got our mounting holes. We could do cool things to this. We could give it a little text annotation here that says power on, power off. I could call these mounting holes. We could add a test pointer to if we wanted. What the heck, let's add a test point. And a good place to add our test point might be right here on the wiper of our pot. So let's go to place symbol. And like everything else with KiCad, you gotta look for it or search for it. I'm gonna go to connector. Let's go down here. How do I know right where this is? That's easy because I just turned off the tape and went hunting for it. So test point. And I can see it here. It gives me a nice little symbol for it. And we're going to put it, I'm going to put it right here. And I'm actually going to, let's take that test point text off there. So I'll double click on it and say, don't show me the test point. I already know it's a test point. So cool, we've got our test point. I think we've got everything we needed. We have our filter capacitor, we have our mounting holes, we have our test point. Now you look at the schematic and you can see that our new components need to be annotated. TP question mark, hole question mark, easy. Go back to annotation. And what I'm going to say is keep the existing annotations. I don't have to. We could reset the existing annotations because we have no investment in our annotation. For my guitar amplifier, we've written manuals around the annotations in here, and I don't want to change those manuals. So for the guitar amplifier, I'm going to say keep the existing annotations. So let's do that. Annotate tells us what it's about to do. All looks good. And we're going to say save. Whoops. We're going to say annotate and close. And now we see hole 1, hole 2, hole 3, hole 4. Our capacitor is now C1. So what do we have to do? We now need a footprint for this capacitor, and we need footprints for the mounting holes and for our test point. So what we're going to do is go over to our assign PCB footprints. So we will do our assigning footprints. And up comes our window, and we see that we've got our footprints for all the other components, but we don't have them for our mounting holes and our capacitor yet. So we'll go down through here and go hunting, and we have mounting hole, have all kinds of nice options here, and let's make sure we can look at them as we go. And in your mini projects, you're going to have mounting holes with clearance for a number 6 screw. And I'm going to leave that up to you to cut through here and find that. And then in your demonstrations, we'll make sure that we can put a number 6 screw through there and it has a nice clearance. What we're going to do for now is we're just going to pick one. And we're going to pick this one right here. Looks about right. Let's actually see how big it is. It's 2.7 millimeters, it says, but I'm not quite sure what that really means. So I'll hit my 0 here, and I see that it's about 1/4 of an inch wide. looks good. I'm not sure what the hole is, but I'm going to leave that up to you to make sure that you get the right holes for your projects. So I'll double click it and you can see here it is, and then I'll do it a few more times. And we have our mounting holes. Now let's get a footprint for our capacitor. And so we'll come up here. This is a pretty easy one. Capacitor, through hole. And I want to use a radial part. And let's take a look at our radials. The radial part is it's a capacitor that is a cylinder, but it goes down on top of the board instead of mounting horizontally. And I'm just going to pick one here, 10 millimeters. That looks good to me. I can see that they're showing the positive here. They have a nice marking for it. And then they have a nice marking for the negative on the silk screen. So that's our capacitor. Finally, let's get the footprint for our test point. So here's our test point right here. And let's just go hunting. Test point, that looks pretty good. So we'll come through here and we see lots of different kind of test points. We can just look at them and a loop. We don't want that. We really want a nice plated hole, something like this. Here's a plated hole, 5 millimeters. That's pretty big. That's about, since there's 25 millimeters in an inch, that's about 1/5 of an inch. That's too big. Let's just make a little test point. I like this one, 2 millimeters or 3 millimeters. That's more like 1/10 of an inch. Let's do the 2 millimeter because what we really want to do is just kind of touch that thing with our scope probe or our voltmeter. So we'll select that test point. And that's going to really make our life easier because now we can just put our lead and it'll kind of fit into that test point while we're making measurements. So now we've done our component associations. So what let's do is let's say OK. And I'm going to save our work. And before I go any further, let's do a design rule check on our schematic and make sure we haven't violated any rules. So I hit that bug here and I got my electrical rules checker. And let's take a look. Run. Wonderful. No errors. So we've got a good schematic. So now what we're going to do is remake our net list. So I'm going to say net, generate net list. It'll put it right on top of the old one. There it is. So now let's go into our PC program, our schematic, our printed circuit board. And I'll zoom out a little bit and let's reload the net list. So I'll hit the net list icon. You can see it up here. And let's see, update PCB. Make sure you're right. Okay. Now what do I see? I see the new components we just added. So here they are. Let's kind of throw them where they need to be. We'll put a mounting hole. Whoops. Got to select them one at a time. Let's put a mounting hole over here, and we'll put a mounting hole over here, and a mounting hole over. I'm using shift roll right now to do this. A mounting hole kind of over here, a mounting hole here. something like that. I'm going to want a nice place to put my filter capacitor. So let's just kind of put it up here because it's kind of near where the power comes into the board. And our test point, we're going to want that somewhere near the potentiometer. And you can see how the rat's nest jumped over here. So we'll put it down here where it's easy to work with. Okay, so I've moved my components around a little bit again, and I have my mounting holes in a nice rectangle. So what I'm going to do now is I'm going to place the alignment target. I'm going to go to Place, Drill and Place Offset, and this is just something that you have to have so that the PC board can be made by the manufacturer. You can put it pretty much anywhere you want, but it's just something that you have to have. So again, I went Place, and it was Drill and Place Offset. So we have that. Uh-oh, I just moved it. Let's move it back roughly where it was. Now the next thing I'm going to do is I'm going to define the outline of my board, because you notice we've been moving components around, but we haven't specified how big our board has to be. As I mentioned before, in a real design, like my little amplifier here, I'll lay out those board dimensions or outlines before I do anything. But here we didn't have to do that. Let me show you how to do it. You want to pick your tool here. You want to come down and work on what we call the edge cuts layer. It's right here over on the right. It says edge cuts. And what I'm going to do is I'm going to first select it. That means that that's my working layer of the board. Layer isn't really a physical layer. It's just a bunch of information. So what's going to happen here is I'm going to draw lines, and these lines are going to end up being the outline of my PC board. So now I'm going to say Add Graphic Lines. So I'm going to pick this tool, and I'm going to use my grid, and I'm going to make my board a little big. So I'll go right over to here. And while I'm over here, I think what I'll do is hit the space bar, and you can see that now my dx and dy are at 0, so I kind of know where I am. So I click, and I'm going to go out here, and it looks like my board will be 4 inches long because dx is 4. I'll click, and then I'll come down, and I make a nice straight line, and I can tell my line is straight because dx is still 4 and dy is 3, so it looks like our board is going to be 4 by 3. So I'll click, I'll go back up here, and you notice here I'm still at a distance of 3. So I'll click again, then I'll come right back up to the top, and I'll double click. And then I'm going to hit escape to stop that process. And what I've done is I've now outline my board. And I've done it on what we call the edge cuts layer, because that's what my tool was. I had that arrow here. Now, something that I like to do before I start routing traces is I just get a look at what my board's going to look like. And I'll show you something really cool. If I go up here to View, and then I hit 3D Viewer, I can take a peek at it and check it out. I can rotate it around. Remember, we picked a socketed part when we did our footprint. There's your socket. There's our LEDs. The green one showed up as red. I'm not going to worry about that. Here's our little our connector. Here are our mounting holes. And we look at this and we say, yeah, this looks okay. Our test point's down here. Frequently, when I'm making a board, I'll look at this 3D visualization and go, ooh, that doesn't look right. This should be over here, that should be over there. So I go back and forth with it until the board really looks right. So this is really useful thing. I can drag it around, I can look at the back. We haven't put any traces down yet, so we don't see any of them. Of course, we see our board is properly outlined. So go ahead and use that 3D viewer all the way through your design process. Okay, so now we're going to do another little piece of housekeeping, which is we want to tell the PC design program what kind of traces we use. Or in other words, if I go over to my Draw Trace tool, in fact, let's just do it. We'll move our working layer from edge cuts up to the back copper. And here is my route traces tool. So let's just route a trace. Let's go from here over to here. Cool, we just routed a trace. That trace is really small. For the kind of boards we make at SDSU, we really don't want our trace to be that small. So what I'm going to do is I'm going to delete it because I don't want it. So I highlight it and hit the delete key. And what I'm going to do is tell the PC design program what I want my traces to look like. So I'm going to go up to File and then Board Setup. And I see all this stuff. And I think it comes up on layers, but let's go to Design Rules. And now I'm going to go to Net Classes. And this is a really cool screen. It's showing me every what we call net on the board. Like here's our 9-volt net. That's all the 9-volt connections. Here's all our ground connections. Here's pad 1 of diode 1. Here's pad 2 of diode 2. I have everything here, and it's showing that it's going to do it using the default net class. So I go up here, and I see default has a track width of about 9.8 mils. And here's the via size, which are the little holes that it uses if it wants to make a connection from the back to the front of the board. The drill size. It's got all these things. Now, what I've done, since I don't want to use that default, what I'm going to do is, and I've already done this, is I defined a new net class called analog. And the way I did that is I just hit the plus here, and it added a new one. In fact, let's get rid of, we'll leave analog. But let's make analog a little bigger. So we're going to leave the clearance at 8 mils. What that means is that if I have less than 8 mils between traces or between things, it's going to complain at me. But let's make our track width a little bigger. Let's make it 12 mils. Just make it a little bit easier to manufacture the board. And so now I've got this net class called analog. What I want to do is I want to make these all analog. See how I can pick either one? So I think I can do this. I can say net class filter, default, and I'm going to assign them to analog. So when I hit this assign to listed nets, let's hope all these change to analog. Hey, look, they did. So now we've told the program that for all of our nets, we want them to be analog. Now I could have as many different net classes as I want. For my guitar amplifier, for the power traces that go to the speaker, I have 1/10 inch traces. They're huge. But for my little signal lines, they're much smaller. So for the guitar amplifier, I have 5 or 6 net classes, and all the different assignments are made down here. But we said, let's just make them all using our analog net class. So now let's look what happens when we draw our trace. I use my trace drawing tool, and I get something a little bigger. Drawing traces is really cool. I go over here, I go up a little bit, I get a nice 45 degrees, and I go right in, and I get a beautiful little trace. So I'm going to Control Z my way out of there. So I've got some work to do now. What I'm going to do is I'm going to go through here and I am going to connect everything. Like for example, this one. Make a nice trace. We'll go up straight, and I can see here that I can now do a straight line. I don't want it to bend there. I want it to bend here. So I'm going to click, and that will nail down this piece, and I'll go over here. Now, I'm drawing traces on the back of the board. So this is like I'm looking through the board, and I can see this trace on the back. Let's draw a trace on the front of the board. So what I'm going to do is I'm going to come over to front copper, and I'll draw this trace. And you can see that it's a different color. So this trace would be on the top of the board. This one would be on the bottom of the board. So why do I have traces on the top and the bottom? Because I can make them cross over each other. They can cross over without shorting. Let's make sure we get this concept down. Here's a trace on the bottom of the board. Here's a trace on the top. Let's go to the 3D viewer. And I go over here and check it out. Here's my trace on the top of the board. Now let's go to the bottom of the board. And I can see my trace on the bottom of the board. See that? I think this is so cool. And this 3D viewer, it's really there to help you. It's just incredibly useful. So my job now is, actually before we go there, am I going to connect all these grounds up with traces? I am not. What I'm going to do is make what's called a ground plane on the board. And what you're going to see is that the ground plane it'll go over the whole board, and then the traces will be cutouts in the ground plane. But the bottom line is, for now, I'm not going to connect all these grounds because I know that I can connect them by just connecting to the plane. So I got a little work to do. I've got to connect all these up. I'm going to do it with my Route Tracks tool. I'm going to do it on the back. I'm going to do it on the front. As I do it, I'm going to find that I goofed when I laid out the placement on some of these parts, and I'm going to just go ahead and move them if I need to. So I'm going to turn on some good music, and I'm going to route some traces. Okay, so I've been just listening to some music and laying traces out. And I just wanted to give you a status update. What you might be able to notice that I did have to juxtapose these resistors around, and that allowed me to get these nice paths that don't cross over to my LEDs. I just had to move them a little bit. You might also notice that all these green traces, they're on the circuit side or the back side of the board. And since the IC will be on the board, I don't want to run traces right under the IC, because if I have to cut those traces, I'll have to lift the IC out. And so I could have made this trace, this red trace, which is actually on the top side of the board. I didn't want it to go under the IC because I may need to cut it or something like that. So I went around this way. So it took me a while. I started out with a few red traces, but eventually I kind of figured out how to make it all work with traces on the back side. Let's see what that's going to do for us by going to the 3D viewer. I'm not just using the 3D viewer because it's fun, really. I'm using it for a good reason. What you can see is the whole top of this board is going to be ground plane. And that means I'm going to have a really good physical ground on this board. The only break in the ground plane we're eventually going to see is this one trace right here. Here, let's turn the board over. This is so cool. And you can see all the traces that I just laid out. Very cool. Now, this would probably, I could probably keep going with this, but this is kind of ugly. In the old days, they didn't like it when you made 45-degree traces like this, because in the photo etching process, it was hard to rinse out the etch in these 45s. Same kind of thing with 90-degree bends like this. So for printed circuit boards, it's always nice to use 45-degree bends wherever you can. You also notice, like right here, these two traces are really close together. Well, if my board house has, bad chemicals or they're a little bit sloppy, I'm going to get failures because of this, because these might short together. So I really ought to move them out because I want to use the cheapest board house I can to make these. Here, these are not really, they're not spaced out evenly, and it's just bothering my eyes. It's not artistic, so I don't like that. Here's a trace that you look at it and you just say it's ugly. So like I said, most of this board would essentially be okay, but it's just not aesthetically very good, and it's not completely manufacturable. So what I'm going to do is I'm going to turn on a little music, and I'm going to just take a little more time and buff it out a little bit better. I'm not going to make it perfect, but I'm going to make it better than it is, just so it's aesthetically nice. If I'm going to make a board and I'm going to show it to an employer when I'm on an interview, I want it to look good. So now I've cleaned this up a little bit. It's still not perfect, but it's better than it was. The next step we're going to do is we're going to add ground plane to this board. Let me explain a little bit about ground plane. I've already mentioned that the ground plane will be an entire copper, we call it a pour, on top here, and we're going to do it on the bottom also. But one of the things that a ground plane does for us is it gives us a nice, solid, electrically low impedance, low inductance ground. And it makes our ground look more like that ideal ground that we use in our circuit analysis class. Here's another reason for using ground plane, and here's why we force you to do it at SDSU. Because if you get prototype boards made by Mark Bruno, our department technician, the way his machine works is unlike a chemical process like a normal PC board house would do. Mark has a prototype facility where we actually mill the copper away. Or in other words, we start off with fiberglass sheets that have copper on both sides, and then we use a mill to mill away all the copper we don't need. If we have to mill away all the copper over here, we're going to go through mill bits like crazy. So if you submit a board to Mark and it doesn't have ground plane on it, he'll ask you to go back and redo it. But so the ground plane is good as far as making your design work better, giving you a higher quality design, but also it's more manufacturable. Now, if you're getting boards made using a photographic process, which is how they're normally done, they also start with a board with copper on the both sides. on both sides, but they use chemicals to etch the copper away. The more copper you got to etch away, the more your product costs. So ground planes are good for lots and lots of reasons. Let me show you how to make them. I'm going to pick my tool here, add filled zones. Let's start off with our ground plane on the top of the board. So I'm going to work on my copper layer, or my top of the board. I'm going to say add filled zones. And let's start one grid mark in here. How about that? I click and it says, okay, you're going to make a filled zone. What net do you want it to connect to? I want it to be ground. And you can see I've specified the front copper layer. So it's going to be ground. So I'll say, okay. And, you know, just to keep everything good, let's hit the space bar so we have an X and Y reference. I'm going to kind of go along here. And I can see my line is straight. Let's go down again. Let's go over here. Go up here. And now I've outlined this layer. Now, as far as my viewing, here are my view options. And you can see that I'm not showing my filled layer. But if I click this, now I can see it. So let's take a look at what we ended up with. We have all copper here. Oh, but look, here's our one trace on the top of the board. Let's look what happened to our ground connections. Here's one. You can see that the ground plane goes right over to our mounting hole. Because remember, our mounting holes are grounded. In fact, here they are, right here. Our holes are grounded, and you can see that they're grounded here. Let's keep looking. Here is our ground connection for our wire. Kind of nice. The PC program is telling us it's a ground trace. And you can see these little fingers coming from the ground plane over to the pad. Now you might ask, why does it have the little fingers? Why doesn't the red just come right over here so we end up with just the little hole? Why do we have to have this opening? Here's why. It's called thermal relief. And if we did not have this opening here, we'd apply solder to this point and the heat would just go out into the ground plane and it would be hard for us to get a good solder joint. So what they do is they have these thermal reliefs so that when we heat this pad, the pad will get hot, but the ground plane will not absorb all the heat. So you see that any connection that goes to ground, let's find, here's one on the IC right here. Sorry, that's not on the IC. Let's look here. Here's our ground pin on our IC. You see how it's isolated thermally, but it does connect to the ground? So that's called thermal relief. That's why we have it. Makes a beautiful ground plane. Now let's put a ground plane on the other side of the board. So I'm going to go to the, I'll go to the back side of the board. And look, when I went to the back side of the board, it's actually showing me those connections that are on the underside of the board. And I will say add filled zones. Might as well just copy this one, right? Ground. Sometimes you'll have power planes where instead of putting ground here, I might put 9 volts or 5 volts or something like that. Very common, but we're going to use ground. So we're just going to kind of trace over this one. Okay, now I have a ground plane on the back side of the board. So looking at the back side, you can see that I have these cutouts in the ground plane for my traces. Why didn't I get ground plane in here? Because I couldn't connect it. Now, if I was able to do what we call plated through via holes, I could just put a couple here. It would connect to the ground plane on the other side, and it would flood this area with ground plane. But a difference between the PC boards that you'll get made professionally and the PC boards that we make at SDSU is we don't have the ability to plate through our holes. Normally with a PC board, if you have a hole, after the hole is drilled, they lay material in the hole and it conducts. But if you get one of our milled boards at San Diego State, you won't get that. What does that mean? It means that when you solder your board, you have to solder on the top layer, and then you have to solder on the bottom layer. If you get a professionally made board like this, you can just solder on one layer, and since the hole is plated all the way through, you'll get that conduction. So let's take a look at our board in the 3D viewer. Here's our ground plane on the top, and here's that one trace. Let's look at our background plane. Here it is. See the clearance? We specified that clearance when we specified our trace widths and clearances. So I'm looking at this board and I'm thinking, this is pretty good. I'm still missing stuff, like I don't have anything on the silk screen here telling me what these holes are, but just for fun, let's go to the design rule checker and see if we've done anything really goofy. So I'm going to go to the bug and say, give me a design rule check. And what it's going to give me is things that are too close to each other, things that are not connected the way the net list specifies, that kind of stuff. So I'm going to hit run. And look at that. I got no errors. And that, I can tell you, rarely happens. The design rule checker is 10 times smarter than I am, and it always catches me on stuff. But this time it didn't catch me. We still have more to do to our board. One thing I want to do is I want to fill this in with ground plane here. The reason is because I don't want to wear out our milling bits at SDSU. And if you give a design like this to Mark Bruno, our department technician, he may throw it back at you and say, we're not milling all this area off. So how do we do that? So let's look at this board a little closer. Right now, we are looking at the back copper. So we're looking at we're looking right through the board at the back. Let's look at the front. So on the front, you can see I have a nice ground plane that goes everywhere. Why didn't I get a ground plane here? The reason I couldn't is because there was no way to connect this ground over here. You can see that you would like it to take this little finger of ground and go through, but that would violate our keep away requirements. So here's what we're going to do. We're going to put down what's called a via. And a via is a little hole that goes through the board, and KiCad thinks that that hole is going to be plated through, because when you get a professionally made board like this one, it will be plated through. But if you get it made at SDSU, it won't. but we're going to put a via in here. So what we're going to do is, here's my add vias. It's right over here. And I'm going to bring this in, and let's put one here. Let's put one here. Let's put one here. So now what I'm going to do is I'm going to tell KiCad to reflood my ground planes. And what I think is going to happen is, since this via is going to go through the board and make a connection to the ground plane on the front, it's also going to connect the ground plane on the back, and we're going to get filled here. So what I want to do is refill my zones. And there's a way to do that directly, but I just kind of know that if I tell it to do a design rule check, it will refill them for me. So here we go. And what's kind of nice is we got no design rule errors. And look what happened. It filled these areas. So we have this little hole here. And if you got a professionally made board, you would have ground right here. If you get one of our SDSU boards, what you need to do is take a little piece of wire. I usually use the end of a resistor lead and just stick it through that hole and solder it on both sides. Because again, your holes are not plated through. So that's what you want to do with an SDSU board. By the way, what's an SDSU board look like? Boy, am I a big fan of SDSU boards. Here's one right here. And you can see that it looks, you can actually see the copper on it. See how it's kind of copper colored, and you see the traces? And the cutouts in here were made with a milling bit. And what you notice about this board is it's copper, where when you look at this board, the professionally made board, it's green. Why is that? The reason is that this board is basically this board, except they put what's called solder resist on it, which is just wonderful stuff. It's like a chemical, and what it does is, if solder comes in contact with it, it just pushes it away. So if I have solder resist between these pads, then I can go down here with a soldering iron, and it's extremely unlikely that I'll get short circuits. If I have this board that has this green solder resist on it. Now, if I do that with one of our SDSU boards, I have no solder resist, and I have a higher probability of getting a short between here. With an SDSU board, I might get a short between here and here because there's no solder resist. So that's the difference between the green stuff here that is covering the copper and this board where there's nothing covering the copper, so it looks like copper. When you guys are doing your mini projects, you'll usually have your board made through SDSU because Mark can turn them around pretty quickly. And what I see when I'm helping you debug them is we usually find solder bridges. You won't have that problem with one of these boards. But on the other hand, Mark will get you your board in a couple of days, and I'm sure you guys will push it out to the limit, and you will need that. Let's look at another difference between, actually, before we leave the subject of solder mask, there's actually a layer on the board. It's not an actual physical layer, but it's part of what we call the Gerber files, which are the files that tell the manufacturer how to make the board. And right here, this front mask and back mask are special files that tell them exactly where to put the solder mask and where not to put it. because of course you want solder mask over all these traces, but you don't want solder mask where you want to solder. So that's this layer here, the front mask and the back mask. Okay, let's look at another difference. If you look at this board, you probably can't see it, but you can see maybe my Siegel Electronics SEA 310 revision Q2, and it's written in white. And that white writing is what we call the silkscreen. That's kind of the traditional name for it, and we still use that name. So the silkscreen is white lettering on the board that it just helps you assemble the board and debug it. Like, you can't really see it here, but the silkscreen kind of outlines all my components, especially these big power transistors here. It actually shows where they go, and it actually shows which power transistor to put in here, because I got to make this thing pretty idiot proof, because it's a kit and I assemble a lot of them myself, so I need that. So if you do an SDSU board, you're not going to get a silkscreen. If you do a professional board, you will get a silkscreen. So let's look at the silkscreen layer. So here it is right here. There's a front silkscreen and a back silkscreen. We typically will not put a silkscreen on the back of the board. Like, if you look at my board, here's the front of the board, you can see the white. You look at the back and you don't see any silkscreen. But let's look at that now. So in this view, I don't see any silkscreen. Why is that? It's because I'm looking at the back of the board. We're looking through the board at the back. But if I say, let's look at the front, hey, look at that. It hides the silkscreen too. Oh no, what do? What I'm going to do is change my view. I'm going to take my cursor over here. Here we're showing all the filled areas. Here I'm going to say, look, I know those areas are filled, so you don't need to show them. And when I do that, I see my silkscreen in blue. So let's take a look at our silkscreen. I see a few problems. First of all, R7, like for example, this reference designator, it's going to be hidden by the components. So I assemble this board and I'm not going to know where R7 is because there's components over it. Same deal down here. Let's see, what else? I don't know what this is. Is this power or is this ground? I don't really know, but I could put a nice marking on the silk screen that would tell me that. So let's fix things up a little bit. So I look at all these reference designators, and what I'm kind of feeling is I could lay them all down here just to the left-hand side of the component, and it'd look pretty nice. So what I'll do is say M for move, and I'll just put that one there. Can I put silk screen over a trace? You bet. Now let's do R9. See how it shows me which component now it's associated with? So if I go up here, I still know it's this resistor. Let's put R9 over here, and R10. Let's line that up a little better. Well, it looks like it won't let me do that because it is left justifying. If I wanted, I could right justify these fields, but I'm not going to go through all that right now. Let's just kind of move them where we want them. So select, move, put it there. 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 If you guys did this the old-fashioned way that I did 30 years ago, where we had to use Mylar and tape and stuff like that, you would appreciate this so much. That's one reason I enjoy doing this so much, because it's come so far. And it used to be really hard, and it used to be expensive, and now it's easy and it's cheap. And you guys got another 30 years to be doing this, which is really cool. So we've got our resistors here, we've got these ones, This doesn't look too good. I think what I'll do is I'll take this R8. Let's move these two over here. No rules that tell me where they have to be, but aesthetically, you want things to be next to the component, right? Duh. So let's see, C1. Let's kind of move it up here. I'll go move, rotate. Kind of shows me where C1 is a little better. What else do we not like here? This looks pretty good. I can see D1, D3, U1 is pretty clear. Let's change our view so we get rid of these courtyards, and let's really look at our silk screen. So I'll go to front courtyard and make that not visible. That's over here. And look what we have on the silk screen. It shows us where the components go, and it shows us which component is going to go in here. Let's look at it on the 3D viewer. So view, 3D viewer, and check it out. We can see our silk screen and see how it's all nicely near the components. I could fix it up a little better. I could put this J3 up here. I could do all kinds of stuff to make it look better, but we kind of got to keep moving because this is a way too long video. But what I do need to do is say what these are. So here's what I'm going to do. I'm going to put it over here. So let's move our J1 reference designator. How about over there? We'll move J2 over here. And let's insert some text on the board. I'm going to use the text tool. That's the T. And I'll click here. And it's going to put the text on the front copper. I don't want this etched in copper. I want it on the silk screen. So I'm going to get out of here and say, oh, I was working on the wrong layer. Let's go down to the silk screen on the front. And now let's do the text. Because it's really cool. I mean, if you want, you could put text right on the copper. For this board that Mark did for me, I actually did put text on the copper because I knew I wouldn't get a silk screen. But it's not something you want to do typically. So we're working our silk screen layer. We're going to say we want some text. And it's showing me what layer it's going to go on. And I'm going to say actually, let's make it match our schematic. Let's look at our schematic. We have bat-9 volts. That's what we want. So let's say bat-9 volts. It's going to be 39 mil, yeah, a little over 1/10 of an inch. Let's just see how good it looks. Yeah, that's too small. I want this to be seen. So what we'll do is let's kind of make it a little bigger. I'll double click it, and we're at 39 width, 39 height. Let's make it a little over twice. Let's go 100. Is this cool? You can set it to whatever you want. Battery 9 volts. I kind of like that, but it's a little big. But, you know, I kind of like the bigness of it. But it means that I really need to kind of move this connector. And I'm good with doing that. So let's do that real quickly. I'm going to get over that connector and click, and it's going to say, hey, what do you want to move because you're near two things? And I'm going to say I want this footprint moved. And let's see what we can do. What if we went in about there? Could we fit our battery 9 volts? M. Move it in. Let's go a little more. Move. I'm going to move this pad a little bit. And so that kind of works. But I'm going to also move this capacitor. Notice the traces aren't moving. I'm going to have to fix that. But I really want my silk screen to be nice here. So we're just going to deal with it. So let's move our ground. So let's see, we'll move this a little more. So aesthetically, things look okay. This is nice. So we have our battery 9 volt. I'm I want that actually a little bigger. Let's make it bold. Italic, orientation, thickness 5.9. Let's make the thickness 8. Okay, that I can see on the silk screen. So now what I'm going to do, instead of going through that twice for my ground connection, let's just duplicate it. Now, if I was in the schematic program, I'd use C for duplicate, but here I'm going to use Control D, or I'm just going to go to the menu. And I'm going to put this right down here, and we're going to call this ground. We'll move it in, kind of justify it with the M. I like that. Let's see what it's going to look like on the 3D view, 3D viewer. Look at that. We got a nice big 9-volt on our silk screen. So no one's going to hook this up reverse polarity. So we got a little cleanup work to do, but that's easy. So what we'll do is we'll get rid of this trace, that trace, that trace. You can see I kind of put these traces in pieces. That's all right. We'll just get rid of them. And now let's redraw that trace. So I'll just kind of go over here. Do I want to draw my trace on the silk screen? No. Let's make sure we draw our trace on the back copper. So we'll go out here. Then let's cut a 45. And we'll go right down in there, and it's beautiful. And now let's come down and fix these traces. So let's see, let's get rid of this trace. Okay, too small. There we go. Now I can do it. Now I can see it. Okay, so what I really need to do is just go over here and then down here. So we'll come here, make our 45, go up here. Do I want to go this close to the negative terminal on the capacitor? No, because I might get a courtyard violation, or I might get a clearance violation, and also I just have a higher chance of a board failure. For example, if you're getting this board made with the milling machine and no solder mask, you put a trace this close, I guarantee you're going to get a short. So don't do that. Put it over here. Give it some room. There we go. Nice, beautiful 45 degrees. I like that. Now let's put this one in, and we'll just go right in there. Beautiful, beautiful. Okay, so now we've fixed that up. We've got a nice piece of silk screen here. Here, as long as we're at it, let's say what this does. Also, let's move this J3. It's bugging me. J3, we're going to go M, and then I'm going to do an R. We're going to put it right here so you know right where J3 is. But what let's do is say what it does. I'm going to duplicate this. I seem to remember it was Control D. Yep. And I'm going to say, let's just call this power, PWR-enable. We're getting creative. And that's really too big. This should be big, but this is too big. Let's make it a little smaller. Let's go 75. 75. That looks better. So now I've got a good silk screen here. So we'll take one more look at this thing with the 3D viewer. I like this. Got my battery, I've got my ground, I've got my power enable. Oh, I know what let's put an adjust down here. So we'll get out of here. I'm going to do a Control D on this one. Control D. I'll put it right here. Can I put silk screen over traces? You bet. We're going to call this adjust. There, now we know what that pot does. Okay, so we'll go back to our 3D viewer. and I see a problem. Let me give you a second and you take a look at this thing. Tell me what the problem is. Problem is, look, we've got a hole here in our ground plane where this used to be. So we have to update our ground plane. And that's easy. Easiest way I know to do it is with the design rule checker. And here we go. And you notice it says refill all zones before performing DRC. So I like that. Okay, so we do this. We got no problems. We got no unconnected items. And if I look at if I re-enable my ground plane, everything is looking pretty good here. So I'm liking this design. We've looked at it on the viewer. It looks really nice. And we've checked it with the design rule checker. Everything's good on the schematic. Everything's good on the board. We had an area where we needed to add a few vias in order to get a nice, good ground plane. And we fixed up our silkscreen. So this board looks like it's pretty good. I want to just make a couple of notes about getting boards made through SDSU. Before you design a board that you plan on asking Mark to make, get in touch with him because he has design rules that you have to follow. He has certain clearance rules and certain hole rules and those kinds of things. Mark has a sheet for that, and you can ask him. And what you want to do is before you even start designing your board, you want to go up here to File and Board Setup. And remember, we've been here. This is where we made our analog trace. And you want to set up your trace so that it meets Mark's requirements. He'll give you these. He'll tell you what the clearance you need is. He'll tell you what the minimum, what your track width should be, or your minimum track width, and your via size, etc. Now you can always make bigger track widths. You'll need that. This little board it's my cool little speaker attenuator board, so I can blast my guitar amplifier without driving all the other professors and everybody nuts. But if you look on here, you'll see some really fat traces because I need them because they're handling a lot of current. But my small traces don't go below Mark's minimums because he can't make those. So before you start making your board, get that information from Mark, go to your board setup, hit your net classes, put in his rules, and let KiCad do the rest. Okay, so now what we're going to do, we've designed our whole board, we know how big it is, everything. Now we're going to process everything into files that can be used for manufacturing. They're called Gerber files. That is an old term. It's not baby food. It's a term that's been around ever since they started doing this on CAD. So here we go. We're going to go up to File, and we're going to go, actually, before we do that, what I'm going to do is let's see. So what I'm going to do here is I'm going to make a Gerber's directory for my Gerber files. These are the manufacturing files. So I'll just call it Gerber's. And we will now say File, Plot. We're not plotting to a printer. We're plotting to files. Plot format, Gerber's. Output directory, KiCad tutorial. We're going to put it in Gerber's. Do I want to use a path relative? You compies know more than I do about that, but I usually use different computers. I use the one at school, the one at home. So yeah, I use relative paths. But what layers do we want to include? Or in other words, what Gerber files do we need? Let's go through the list. Front copper, back copper. You bet. Those are our traces and our ground plane. Front adhesive, back adhesive. We don't need adhesives because we're not doing surface mount. And we don't need paste layers because we're not doing surface mount. I'm going to leave them because it doesn't hurt to make them. Front silk screen, you bet we need that. Back silk screen, there's no back silk screen. Front solder mask, absolutely need that. Mark won't use that, but a professional PC board manufacturer will. Back mask, you bet. It has to know where it puts mask and where not to put solder mask. Edge cuts, absolutely. We need that because it tells them how to cut the board and dimension the board. So there are the files we need, and we need one more file here. We need a drill file, which tells it where to drill all the holes. So I'm going to go down here to generate drill file, and we're going to use the PostScript format. PostScript was around before any of you were even born, but it works perfectly well and everybody still uses it. So we're good. So it's going to go in my Gerber file and I'll say generate drill file. Cool. And then close this window. And now I'm going to say plot all these Gerbers. Here we go. So it's plotted them. So let's go look in Explorer. What do we have? We have the back copper. We have the mask, we have the paste, we have the edge cuts. These are all files. And then here are our drill files. So all these files will tell any board manufacturer how to make this board. So here's what we're going to do. I'm going to put these in a zip file, and then we're going to go out to the internet to a board manufacturer and submit them. So let's make our compressed folder, and we're going to call it KiCad tutorial Dorr. So here we go. And now I'm going to take all this stuff and I'm going to just stick it in here. Okay, let's look in here. Yep, we got it. So now what we're going to do is we're going to go out to the internet and we're going to go to my favorite board manufacturer, JLC PCB. I like these folks because they're out of China and their boards are so cheap. I can get 10 of these boards shipped in a week to me for about 35 bucks. It's just insanely cheap. Why is it so cheap? Because they can't make the kind of component density that goes in your cell phone. So what? The kind of stuff we do, they do beautifully. So now we're at their website. So I'm going to say, get a quote. And it is going to ask me, quote, what? So it says, add your Gerber file. They accept zips. So add your Gerber file. And let's just go over here. And here is my zip file. So I'm going to say open. This is really cool. So they're uploading the files. And look at this. From what I just uploaded, they're showing me what I just put in. So it's showing me my component side. It's showing my circuit side. And so let's go back here. How many layers is the board? It's 2 layers. It has a top layer and a bottom layer. Here's the dimensions. And let's say we want 5 of these because it's a mini project. And we can pick our color. I think green is the cheapest because that's what they do the most. 1 ounce. What that means is it's the copper thickness. So it's like 1 ounce per square foot. Why is that important? Because when I'm making power leads for my speaker, I need to know how thick they are because I need to know the resistance of my traces. 1 ounce is pretty common. You're good with that. In other words, their defaults are pretty good here. So what it's saying here is $2. So shipping estimate is going to be $7. So now I can go save to cart and all the normal stuff. It'll give me the shipping options. But bottom line, what this is showing me is that they understand our format and they can make this board for us. So you can either give those Gerbers to Mark, or you can give those Gerbers to a place like JLC PCB. If you go through Mark, you're going to get a board that looks like this. And you're going to have to solder the top and the bottom of your components. You're going to have to solder the top and the bottom of those vias that we put in here. And without solder mask, you may have some debugging headaches because you'll get solder bridges. But it's very common. Most students use our SDSU boards for their mini projects. One thing I forgot to do when we made our board is I forgot to put a revision on it. What Mark likes to see is your name and a revision, revision A, revision B. The reason he insists on that is because you guys will make the first one and then it won't work, and then you'll make a new one and you'll want to say, oh, here's the new one. And Mark will say, I can't work with new one. I need a revision number. So you'll want to put that revision number on the silk screen. So there you have it, folks. As you can see, I'm never going to make videos for a living, but in this video, we've made a simple board and we've really slogged through it, but we've gone through every step you need to make a schematic and then get a board made. I hope you guys enjoy this as much as I do. I really enjoy making boards. I love making these boards for my guitar amplifier, and then when I'm watching a really good guitar player shred on it, I'm just envisioning all those electrons going through all those traces, and it's just something I really enjoy. It's also a really, really good skill. Most old people, we're still stuck in the mindset that making PC boards is hard. I was in that mindset until one of my students really pushed on me to start doing it myself. And what that means is when you go into a company and you say, lay out boards, yeah, I can lay out boards. I do it on KiCad, but Altium, KiCad, DX Designer, they're all very similar to each other. So yeah, I know how to lay out boards. I know what a silk screen is. I know what a solder mask is. I know what a through hole, what a plated via is. So this is a really good skill. So go out and make us some good mini projects, and we will see you in class.